right, scholars. All right, let's move on. Let's begin. Hey, what's the difference between a hot cup of coffee and a cold cup of coffee? We say temperature. What's it mean? Something different at the atomic level? Hot cup of coffee, cold cup of coffee? In the hot cup of coffee, there's more activity. The molecules are jiggling faster. They have more energy of motion. We got a name for energy of motion. What do we call it? Kinetic energy. There's more kinetic energy in the molecules in a hot cup of coffee than a cold. You know that. That's what it means to say that something's hot, that it has more energy. We might say more thermal energy. More strictly speaking, we'll say more internal energy internal to the system. So there's much more internal energy in a hot cup of coffee than a cold cup of coffee. Hey, what's got more internal energy, a hot cup of coffee or an iceberg floating down at the Antarctica? Check your neighbor for an estimate. A humongous iceberg or a small hot cup of coffee? Which has the more internal energy? All the energy combined. What would it be, gang?
Yeah, but ice is frozen.
How many say the hot cup of coffee still has more kinetic energy of all those molecules and those zillions and zillions of come on, no, it's the other way around, gang. It turns out there's more internal energy in a humongous iceberg simply because there are more molecules jiggling. You know, add up all the energies, you're going to get a greater amount, see? But when we talk about the energy per molecule, we're talking about an idea that begins with T. Try it. Temperature, yeah. Temperature has to do with the energy per molecule. See? So the energy per molecule in a hot cup of coffee is a lot more than the energy per molecule in a hunk of ice. Ain't that true? Yep. So we see there's a difference between temperature and total amount of energy. Temperature is an average energy per molecule kind of, yeah? We measure internal energy or any kind of energy in joules or in heat units, calories, joules, same. What is it, 4.186 joules equals 1 calorie, something like that. But calories and joules are both a unit of energy. And temperature is measured in degrees. Degrees. How hot something is has to do with number of degrees, and that's different altogether. It turns out that the number of degrees, that the amount of temperature has to do with the kinetic energy of motion. Well, usually things, when you heat them up, they expand. Most things will expand when heated. Liquids, gases, solids all expand. Guess which expands more, a gas or a liquid for the same change in temperature? Well, it turns out a gas. I could take a balloon and hold it over a stove. You could see that thing grow. But if I take a gallon of water and hold it over a stove, you don't see it grow very much. It does. And how about solids? How do they expand compared to gases? Not so much, but they expand nevertheless. So liquids expand, and because liquids expand when they're heated, you could make thermal meters. Thermal meters. Let me show you an example of one. You might do this in the lab part of the class. You might have a glass tube like this. And in that glass tube you have some mercury or some alcohol, colored alcohol. You have it in here, say like that, okay? And it might come up to this particular level. Now what you do is you put that thermal meter, which is a hunk of glass about this long with a reservoir at the bottom, you put that in a bath of ice cubes that are melting. Melting ice. When you do that, the temperature of this becomes the same as the temperature of this, because the slow-moving ice molecules or slow-moving water molecules over here impart only a little energy to here, or if this is hotter, by the way, it would send energy this way and heat up the water. You know, you can't have your thermometer too big. How about you get a thermometer this big and you're measuring this much water? Come on, who's measuring what, right? In fact, you know, people say a thermometer measures its own temperature. And that's true, because any two things put together will come to the same temperature. And that's what happens here. So at 0 degrees, there'd be a certain elevation of the liquid in there. And you could take a little glass file and you could put a little mark there if you're in the lab part of the course and say that's the level that corresponds to this particular temperature of water. Now take that ice out of there. Now take the water and heat it up until it's boiling. Boiling water, okay? Boiling water. What's the boiling water molecules do to that glass? Bam, bam, bam. They're really hitting. They're hitting with a lot of kinetic energy. And they bang into the glass with a lot of kinetic energy. What do the molecules in the glass do? They start banging too. What do they do to the neighbor? Bang, bang, bang. It cascades right through. Next chapter, we'll call that conduction, where the energy cascades with molecular impact. Bam, 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 right? And finally, what do you know? The liquid in there, that stuff is being shaken too. And when it's shaken, what's it do? It climbs the tube. It climbs the tube, climbs, and it finally settles off and stops. And guess where you make your second scratch? One guess. No, not down here. Not up here. Guess, gang. Right here. You put a scratch right in there. Okay? Now you got, and you can call this the temperature of boiling water. And we can call that 100. We can call this scratch down here 0. Now we got to make 100 scratches, evenly spaced. So we get 100 grades. 100 grades. Do you guys know what the prefix 100th is? What's a hundredth of a dollar? No, not a penny. A what? Cent. A cent. Okay, so we call this a centigrade thermometer. Centigrade, because 100 equals centi. Huh? So we get 100th grade. We get a centigrade thermometer. So we measure these things in centigrade degrees. See what I'm saying? So if you take this and put this in some other bath of water and the level comes up to the same, you know it has the same temperature as the initial one. So that's a centigrade thermometer. Now, in America, we don't always use the centigrade thermometer. Americans are a little bit more innovative, a little bit more maybe off the wall sometimes. American type do this, repeat the same experiment. And what the American type does is the American type puts this in here and gets a scratch there. And he doesn't have to call it 0. You call it any number you want, really, so long as you make them all the same way. Give me a number at random. 32. All right, 32. You could call that 32, okay? I mean, what's so special about 0, yeah? Now, you put this in the boiling water, you the 32, bam, bam, bam. Now you put it in boiling water, bam, 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 really hitting, huh? Well, then climb up, scratch. You want to put 100 there? You want to wimp out and put 100 like everyone else does? Go ahead. But let's suppose you say, hey, let's get off the beaten path. Take any, give me a number at random, any number. 212. All right, 212. All right, 212. All right. Now, what do we call that thermometer? An American thermometer, okay? Okay? With that, and what we're saying is the boiling point of water is 212 degrees. And the freezing point of water is 32 degrees, okay? Now, here's the problem, gang. You got to cut up equal number of, you got scratches in there. How many scratches are you going to have between 212 and 32? Yeah, you can't do it. Anyone got a calculator? Nobody. Anyone do it? Maybe pencil and paper? How many scratches between here and here? This requires an arithmetic operation. It requires taking 32 away from 212. The 2's all right, but look at the 3. You got to subtract the 3 from a 1. You got to do some carrying. All right, let me tell you again. I've done it before. It's 180. 180. So you got 180 scratches. Does anyone know what the prefix 180th is? A Farren. That's right, a Farren. Engineer types know that. That's a Farren. So we call this a Fahrenheit thermometer. Okay? You ever hear of Fahrenheit? We don't call it a Fahrenheit thermometer because we name this thermometer after the man who invented this scale. In honor of him, we name it for him. So it's not a Fahrenheit. Does anyone know the name of that guy? James J. James J. Height. Mr. Height is the one that done that. So we call it a Fahrenheit thermometer. You be believing this? Just toying around with you guys a little bit, okay? But anyway, this is Fahrenheit thermometer is measured in smaller degrees, see? Smaller degrees. You get 180 of those suckers in between freezing and melting at the boiling point. In the Celsius, you got 100. They're spread out more. So what's more accurate to the degree, Fahrenheit or centigrade? Fahrenheit, see? Because centigrade, you got to deal with more fractions. But Fahrenheit has more spaces, finer tuning. So those are the two thermometers. Then there's another that we'll talk about when we get up to thermodynamics, and that's called the Kelvin scale. And the Kelvin scale is named after some dude by the name of James J. Scale. You got it. You got it. All right. All right. So we have those kinds of ways of measuring temperature, the average kinetic energy per molecule of things. Here's a nice distinction between temperature and internal energy, or loosely speaking, heat content. This used to bother me when I was a kid. You know those 4th of July sparklers? You light them and they all those white hot sparks going out? You know what the temperature of those sparks are? More than 1,000 degrees Celsius. More than 1,000 degrees. Is that hot or cold?
Cold.
H. No. Begin with the H. Hot, okay? Those are hot sparks, gang. Over 1,000 degrees Celsius. You ever see little kids with those little sparklers home like, hey, look at the sparkler, honey, and the damn sparks are bouncing off the kid's eyeballs and his cheeks and everything? And does the kid scream? The kid's okay. And I said, wait a minute, the temperature of those sparks, it's white hot temperature. Enormously high temperature. How come the kid ain't hurt? And it has to do with the definition of temperature. Proportional to energy per molecule? Every molecule got a humongous amount of energy. But how many molecules in that little spark? Not so many. So what's the total energy of that spark? Not so much. Below the kid's threshold of feeling. So although the temperature is high, the heat content, the internal energy of the spark is very low. Later on, we'll do a similar thing. I'm going to rub a balloon against my head. And I'm going to tell you guys, this balloon got like thousands of volts. But we'll learn there that voltage is sort of like electrical pressures. It's energy per charge. Not many charges, so not much total energy. With a sparkler, not many molecules, so not much total energy burn in the face. So temperature and heat content or internal energy, two different things. And by the way, we got a definition for heat that departs from the commonplace definition that you have on the outside. And that is, we say that heat is the energy that flows from one object to another by virtue of a temperature difference. So heat is always energy in transit, strictly speaking. When the physicist talks about heat, the physicist is talking about energy in transit. Total amount of energy, physicist is talking about internal energy. And the energy per molecule, the physicist is talking about an idea to begin with a check your neighbor. Begins with a T, gang. Try it. Temperature. Temperature. There's a difference between temperature, which is measured in degrees, and heat, which is measured in calories or joules. Got such thing? Different things heat up different rates. You're at home. You got your stove. If it's an electric stove, red hot. You take a frying pan. Take the frying pan, put it on the stove. Turn around, come back, put your hand in the frying pan. Ooh, you burn yourself. Tattoo city, honey. You have burned yourself. Take that same frying pan. This time, pour a little water in it. Now put the water-filled frying pan on the stove. Turn around, telephone ring. Was it? No, I don't want any aluminum siding on my house. Thank you anyway. Boom. You come back later, a few minutes later, put your hand in the water. It's okay? It's okay? If you can do that, you can do that. It's okay. Now, I got a question for you. Which do you suppose has more internal energy? Which has absorbed more heat? The frying pan empty or the frying pan with the water in it? Think. I'm not asking which has got the higher temperature. I'm asking a different question. I'm saying which has absorbed the most heat? And your neighbor says, what's the answer, gang? The water. The water has absorbed more heat. But you know what? It's not as hot. The temperature's not so high. So some substances will absorb an awful lot of heat for only a small change in temperature. Iron, put a little heat energy in it, whoop, the temperature soars. But water, take a lot of heat energy to make the temperature higher. That has to do with temperature being the translational back and forth motion of the molecules. When you heat up iron, the little electrons in there start zapping back and forth, make the molecules move back and forth. Translational kinetic energy, that temperature goes up very quickly. But it turns out when you heat up the water, that water is a little funny little devil there. That water doesn't just shake back and forth. What the water does, it puckers in and out. And it gets into, look, what's called internal rotational states. And the hydrogen bonding makes them all fixed together so they don't shake so much, but they have the energy in a potential form. And so that doesn't drive a thermometer up very much at all. So you can put an awful lot of heat in water and the temperature goes up a little bit. We say water stores an enormous capacity of heat for small temperature rises. We're talking about specific heat. Physicists say, hey, water got a high specific heat. Means it'll take in a lot of heat for a small temperature change. That's why you use water in your radiator in your car. What do you want the water to do in your car? You want it to absorb that heat energy from your car so it doesn't melt, right? And so a little bit of water will absorb a lot of heat energy. And the temperature doesn't just go up and boil away on you either. Turns out water will absorb a whole calorie of heat energy for every gram that undergoes 1 degree temperature change, 1 Celsius degree. Specific heat of water, 1 calorie per gram degree Celsius. So water, a big specific heat compared to other things. You can reach in a pan in an oven and take out with your bare hands an aluminum dish. The TV dinners, you've done that. You can't hold on it for a long time, but you can take it out quickly and put it down, and your hands are okay. Because it turns out what? That aluminum dish has not absorbed as much energy for its high temperature change as something like water would. Or when you're eating foods, some foods you eat, you can eat very, very hot comfortably. There's not very much energy in there. In some foods, especially with water, like the inside of pie filling, eat it, and ooh, you burn yourself. Because that high temperature has an awful lot more energy in it than say something like the aluminum foil on a TV dinner, something like that. Different things have different specific heats. I know water has a high specific heat. I remember when I was a kid. When I was a kid, I grew up in the outskirts of Boston, and in the wintertime, gang, it is cold. And upstairs, we had one radiator in the house, and that was in the bathroom. And the bedrooms were really, really cold. You had to get the heat from downstairs that would come up by a process we'll later call convection, okay? Or it would have to come a little bit from that radiator and migrate into the rooms. Anyway, it was cold, and on cold nights, we had a way of getting through. What my mother would do is downstairs in the kitchen, she would cook a great big bucket of water. Not a bucket, but a great big pan. What do you call it? Pail. You know what I'm talking about. Container, okay? A container of water. It'd take a long time to heat that water up, gang. A long time to heat that water up. And she'd take that water and she'd pour it into a jug. And that jug was what we call the hot water bottle. And that jug was like a clay jug, and she'd fill it really hot. I mean, really, really high. And you put your feet on it, you're going to burn. So I put a towel on there. And you go upstairs and you put it in your bed, you put it at the bottom, and you put your feet on it. And we had an old adage that if your feet are warm, you're warm, okay? When your feet get cold at night, you're sleeping on it. You can't, it's a tough city, okay? But you put your feet in that hot water bottle, it's okay. And in the middle of the night, it gets so it's not quite so warm, you reach down, you take the towel off, and you put your feet right on the bare, and you get all through the night. It's okay. I didn't know anything about physics then, but looking back, I could see water get an enormously high specific heat, meaning an awful lot of calories in that jug of water. And those calories are delivered slowly and slowly to my feet. So it's kind of neat. So high specific heat for water. The high specific heat of water has to do with different climates throughout the world. Here I've got a globe here. Let's take a look at this. Go over to England. Here's England right here. Go to England in the summertime. How's the weather in England in the summertime? Okay or not okay? Begin with an O. It's okay, it's tolerable. But honey, England doesn't really get very much sunshine. Because if you keep your finger on England and turn the globe, I can't do that now, you're over here in Labrador. What's the climate like in Labrador in the Hudson Bay? Okay or not okay? Well, it's relative. It depends what you call okay? But honey, it is, begin with a C, end with a D. It's cold. It's very, very cold climate there. But you know what? It's the same latitude as England. So why? England's surrounded by what? Begin with a W. Water. And that water has a high specific heat. And that water is really heated up down here by the equator, isn't it? Water's heated up down here all year round, right? And that water drifts north in what's called the Gulf Stream. I guess someone near the Gulf must have named it, yeah? And that water drifts north. And how many say, oh, the water must cool off real quickly? No, the water don't cool out quickly. That water migrates right up through here, and comes off here in the North Atlantic, and there it settles. And you know what? The water does cool down. Conservation of energy. To say the water cools down is to say something else got a WU. Warm up. All right, yeah. See that, gang? So when the water cools, the energy got to go somewhere, and so it goes to the air. And the winds at these latitudes are westerly. And the winds go this way and warms up all of England. But look at poor Labrador over here, or these regions up here, Saskatchewan, way up in here. That's up here. Man, there's no water. There's no water that's cooling off. Now, I will submit, on this side of the Hudson Bay, you should have a better climate, a warmer climate, than on this side of the Hudson Bay, because the winds are going this way. Same thing as San Francisco. San Francisco has palm trees. The same latitude as San Francisco is Washington, D.C. Honey, the best they can do are cherry trees, okay? No palm trees, and the only palm trees in Washington, D.C. are in the hotel lobbies, okay? Right? But we have palm trees in San Francisco. And why is that? Same latitude, same amount of sunshine per unit area, see? But it turns out, well, we got the Gulf Stream, not the Gulf Stream, we've got the ocean out here. Now that ocean, if that ocean in the wintertime cools down a little bit, what's the air do? Begin with WU. Warm up, okay? And if it blows this way, what's it hit? Begin with a C. A-L. F-O-R-N-I. So California is a much warmer place in the winter than East Coast communities of the same latitude. Ain't that neat? Okay. In fact, any place that's surrounded by water has just about the same temperature all year round. How about the best place in the world? Right here. Okay. That's Hawaii, huh? The Hawaiian Islands, okay? The Hawaiian Islands, about the same temperature all year round. But not only the Hawaiian Islands. Iceland. Iceland, way up here, has about the same temperature all year round. Yeah. Surrounded by water, okay? When it tends to be cold, the cooling water will heat it up. When it tends to be hot, the warming water will cool it down. So water acts as a moderator. Aren't you glad that water has a high specific heat? Yum yum. Has to do with the world we live in, yeah? Something else about water kind of neat too. Water is the only substance, the only common substance that will expand when you change it from the liquid state to the solid state. Did you guys know that? See, ice will float on top of water. Why? During the freezing, the ice must have puffed out. The ice puffs out. And why does the ice puff out? You guys ever see snowflakes? Leave after school today and go out and catch the snowflakes. Let them fall on your sleeves, okay? If you got a black sleeve, you look at the snowflake really carefully. Hey, son of a gunman, the snowflake got 6 sides. Hey, this one gets 6 sides too. Hey, they all get 6 sides. I wonder why. Your friend said, well, there's probably no reason for that. It's just characteristic of snowflakes. What do you say? Honey, there's got to be a reason. And the reason for the 6-sidedness of the snowflakes has to do with the way the H2O molecules pack together in their least energy configuration. And as they all pack together and they form hexagons. Do you see that in the textbook? I think it's on page 263. And they form these hexagon structures with an open space in the middle. See what that means? A snowflake takes up more room in the snowflake form than if you melt it and turn it back to water. You turn it back to water, the molecules will cave in and occupy that empty spot. It's like a brick building. A brick building occupies more space when it's in its constructed configuration than if you shake it so hard you shake all the bricks and they cave in. The pile of bricks is less voluminous than the brick building was before it caved. Same thing with ice, gang. So water forms an open structure in its crystalline form. And that's kind of nice. It makes ice less dense than water, and the ice will float. So you can go ice skating, gang. Some people are kind of good at facts and figures. Does anyone here know when it was that Christopher Columbus sailed for America? You probably don't be knowing that year. How many people happen to know the year from their history? Can I have a show of hands? 1, 2, 3, 4, 5, 6, 7, 8 scholars. Okay. It happened to be 1492, gang. Do anyone happen to know when the Declaration of Independence was signed in the United States? It's a particular date. Some people have it engraved in their heads, and some people say, oh, I don't be knowing such thing. When was the Declaration of Independence signed? Anyone know what year? Like, I have a show of hands. I want to see who you is. Show of hands. Well, we got almost half the scholastic class here. It turns out to be 1776. Some of us are good for remembering figures and some of us aren't. Let's try something different. The temperature at the bottom of Lake Superior, New Year's Eve, 1900. Does anyone in here happen to know what the temperature at the bottom of that lake was at that time? 1, 2, 3, 4, 5, 6, even less people than knew when the Declaration of Independence was signed. And what did the temperature happen to be, gang? Say again? 4 degrees Celsius. You're right. 4 degrees centigrade, right? Celsius, centigrade, same, gang. That's right, right on. Does anyone happen to know what the temperature at the bottom of Lake Tahoe? That's over a ½ kilometer deep. Lake Superior is almost a ½ kilometer deep. But Lake Tahoe in California, does anyone here happen to know the exact figure of the temperature at the bottom of that lake right now? 1, 2, 3, 4. Oh, the same hands. What's the answer, gang? Shirley? 4 degrees Celsius. That's right. Hey, outside the building here, when I came in, there was a big puddle. Does anyone happen to know what the temperature is at the bottom of that puddle outside right now?
28.
No, it ain't 4 degrees Celsius. No, no. It's not. The temperature of the puddle is the same as the temperature of the air outside, okay? They're all the same temperature. But how about a deep body of lake, gang? Do you know why the bottom of those lakes are 4 degrees Celsius all year round, all the time? First of all, they're at latitudes where there's 4-degree weather in the wintertime. So let me ask you a question. Oh, you don't know about 4 degrees yet. 4 degrees. I got to tell you something about 4-degree water. 4-degree water is like dense or not dense? Dense or dense?
Dense.
Honey, 4-degree water is the densest water you can get. Because water has different densities at different temperatures. See, if you heat some water up, wouldn't the volume get more and more and more? You know that's true, because if you put a pan of water in the stove and fill it brim fill, and then turn on the stove, what's the water going to do, gang? Begin with OF. Overflow. The water's going to expand, see? Okay? So the water, when it expands, it'll have more volume for the same weight. It'll be what? Less dense. So density depends on temperature. But it turns out ice got less density than boiling water. Now, how come? Because it forms all those open structures. I'm going to make a graph here, and this graph is volume of water versus temperature. I'm going to consider some ice water, not ice, not solid ice water. And that ice water has a particular volume like this. Now, there are two things going to happen when I heat the ice water. Number one is, when you heat anything, the molecules will start jiggling faster, and take up more room. So there's sort of an expansion, okay? Which is to say, as the temperature goes up, the volume increases. That's true of most everything that you heat up. It'll grow bigger and bigger the faster the molecules shake, okay? But something else happens with the water that doesn't happen with other fluids, other liquids. And what happens is those it turns out in that 0-degree water, you got a whole lot of those open crystals. It's like a microscopic slush. And that microscopic slush, when you start heating it, what does the slush do? It caves in. And when it caves in, does it take up more room or less room? Less room. And so when you heat water, due to the microscopic slush that's in there, starts caving in, the water starts to go down. And so you got two things going on. A cave-in as temperature increases, and an increase in volume as temperature increases. Put them together, and when you combine them, you get something like this. And right here, that's 4 degrees. 4 degrees above freezing. Has the least volume. See that? And then above 4 degrees, it starts to go up. You still got some ice crystals crunching in there, but this part here is overtaking it, and it goes like that. So you have this dip in the curve, which turns out to be very interesting. Very interesting. That dip in the curve has to do with the fact that on these deep lakes, like Lake Superior and Lake Tahoe, I don't care how cold the winter gets, gang, you're not going to get any ice on those lakes. And let's see why. A shallow lake, yeah, but a deep lake, no. I've been up to Lake Tahoe, and I've asked the people, hey, how come you got no ice on the lake? And they say, oh, it's too deep. Go to Lake Donna down the road there. You got plenty. You go ice skating there. You're not going to skate in Tahoe, gang. Tahoe never freezes over. How come? Because it's too deep. Which kind of begs the question, well, how come too deep means it won't freeze? So we say, hey, I'm not a physics type. Just keep moving, honey, okay? But let's look at it. We are physics types. And we want to see if there's a reason why that deep lake won't freeze. And it turns out it has to do with what we're talking about right now. Let's take a look. Here's the lake. Okay, let me draw this. Here's a lake. Let's suppose that lake is 10 degrees above freezing. So it's not going to... What's the temperature at which freezing takes place, gang? 0. Okay, so if I'm going to freeze some water, I got to bring it from 10 down to 0, yeah? Okay, let's suppose out here, this is the air, let's suppose it's 50 degrees below 0. I mean cold. And that cold air blows over the top of the lake. How many people think that cold air blowing over the top of the lake is going to make the temperature at the surface go up? Show of hands. Good, nobody. How many say that cold air would probably make the surface temperature go down? Show of hands. Well, almost everyone. Oh, hey, we got everybody? Does everyone think that? If you got 50 degrees below zero air blow over you, you're going to get colder, not warmer? Is that remarkable? Come on, come on. There's nothing remarkable about that. But I'll show you a remarkable consequence of that. Turns to 9. We'll do it by incremental steps. 9 degrees. The wind. 8. Can you see that makes sense? What do we got to get to? 0, yeah?
0.
Okay. Do anyone see something unusual here? Let me ask you a question. If I take a rock and throw it in that lake, what's the rock going to do? How many say, oh, it'll probably float? The rock is going to sink, man. And why is the rock going to sink? Well, it's characteristic of the rock just to sink. Come on, why does the rock sink? Because it's more dense than the water, right? How about this 4-degree water? What's it going to do, gang? Begin with an S, end with an ink.
Sink.
Sink. Sink to the what? The bottom. Here's your 4-degree water down here. What takes its place? Begin with a T. 10. By now it's February. Okay? Get the idea? Honey, we're going to need a long winter to get to that lake. But now it's March. How much time do we have? I get mixed up, okay? You get the idea. What happened at 4, honey? By now it's May. It's April and May. We're running out of winter. You can't get a deep, deep lake to get on 4 degrees. Before you can get any 3-degree water, never mind 0, what are you going to turn the whole lake to?
4.
And let's suppose we had like a big meteor hit or something and we get like no sunshine for about 4 or 5 years. Then we'd get something like this. Keep doing the same thing. Then pretty soon, after a couple of years of that, then it would all be 4. Honey, that's a lot of energy taken away by that cold wind. When you get the whole lake 4 degrees Celsius, then, and only then, that's the first 3-degree water that lake has seen, gang. Does it stay there or does it sink? It stays there. Because what's down below is more dense. The lighter, the less dense will float on top of the more dense. That makes sense? Watch. Now we got 0-degree water. Those of you who are sitting close today will see something that those in the back of the room might not see. But watch very carefully to what happens to the water at the top. Do you see that? Did you guys see that? Did you see the crystals form? Again. See, it's a little thicker? Did you see those crystals form at the top? Do you see now why ice forms at the top of a body of water? Ain't that neat? So now you start to get some ice, and the ice floats on top of the other water. But you see why you have to have, why that only happens with a shallow, you go up to Lake Tahoe and you take a saucer full of water, put it outside your motel room, come in and play checkers half the game and go back there, boom, that water is solid ice. And you look out at the lake and it stays water all the time. Now you'd be seeing why. A reason for those sort of things.
How come then, like, glacier water is rapids? Like some rapids only about like 4 or 5 feet deep.
Catch that again, say again.
How come some glacier waters, like rapids, only about 4 or 5 deep? I know they're moving, but how come they don't freeze? Because they're like ice, that's ice cold.
Ah, how come moving water doesn't freeze? Yeah, how come moving water doesn't freeze? Well, sometimes moving water does freeze.
You just usually see it on the outside edges though, right by the land. You never see it, the whole thing freeze over.
Yeah. Well, gee, that seemed like a pretty easy question to answer, doesn't it? Wouldn't you expect your teacher would be able to give you, oh, the reason for that is blah, 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 blah. Well, I don't think I can give you a good answer for that, other than say it, the crystals can't, they're not a good answer. Can we still be friends?
Oh, no.
Oh, that did it? Okay. Try another question. Give me one that says I can answer. Okay. Hey, let's talk about this expansion and this expansion under different temperatures and everything. We got something here that's kind of neat today. Ted, could you give me a hand? Talk about low temperatures. Ted's brought over here some liquid nitrogen. This liquid nitrogen is about 190 degrees below 0 Celsius. Really, really cold. Almost 80 degrees above the absolute 0 temperature. Now, can we have a volunteer jam their hand in there for about 5 minutes? Okay. Nobody gonna do that, right?
What do you want to do first?
Okay. Let's show how the let's show how the volume of something will change. Here's an air-filled balloon, gang. Okay. What's going to happen to the volume when it gets cold? How many say, "Oh, it's going to expand"? Stand up. And what happens to the volume, gang? Now it's going to start to warm up to air temperature. What happened to the volume? What happened to the volume? We bring it above air temperature? Bring it a little closer, Ted.
Close?
Yeah. Okay. Let's try the flour. This is a flour Ted found out in the ground. It's kind of nice and limp, right? Kind of limp, isn't it? Okay. Well, what happens if we slow those molecules down?
Why does it fizzle like that?
Yeah, why did it fizzle like that? What's going on? Oh, gang, did you see such a thing? Look at that, gang.
If you stuck your hand in there and hit it against the table, would it do the same thing?
Yes. Can we have a volunteer, please? Unfortunately, it would, yeah.
Another one?
All right.
Would a penny break? You want to try it?
Okay. Ted's got a little,
Let's see if I can do this. I did this a long time ago.
What was that?
Now, I got a friend of mine, his name is Gerald Walker, who does something that I don't have the guts to do. Gerald takes this stuff and drinks a little bit and blows out. I ain't gonna do that, gang. Ted's doing pretty good, yeah? Guess who's got the courage of the two of us?
This is what I was thinking.
Go on, try one. Here's what you get for being a TA.
What'd you do? Did you eat it? Is that right? Did you put it in your mouth?
What you do is you hold it using your tongue, or hold it over your teeth, and then just blow out over the top of it. I only brought the floor, so if anyone has any spare.
I didn't see how you did that, Ted. I hope you're right here.
You want me to? Oh, I have an extra one. You
My
want me to
teeth?
do it first?
Yeah, do it first. Let me look and see
Okay.
what you're doing.
You pick it up.
Yeah. Anyone hungry?
Oh, one more.
We'll do this at the party, gang.
It's a little cool, yeah. That's why you don't stick it on your tongue for a long time. But it's the same story with the white hot spark. It's not real cold for a long time. There you go.
Thank you, Ted. Whole day, man. Whole day. Okay.
Yeah. How death-defying are we going to be here?
It's quite toxic.
We got a penny.
What do you suppose happened to the size of that penny that we put in here, gang? If you had some calipers, you measured the diameter, what would happen to the diameter when it's cold? Get larger or smaller? Smaller. Going to shrink, right?
Does that water warm up after a while after it's been out in the air?
Oh, it's not water. This is
water?
liquid nitrogen.
Okay, well, liquid nitrogen.
Hold on.
Does it warm up though after?
Oh, yeah, it warmed up, yeah.
It's boiling.
boiling
what
right now.
That's what this stuff
It's
is.
boiling right now.
You wanted to see if this was going to break, right? No. That's going to be
That's a little
real on the much side. You want this back?
We'll learn later on. The copper is a very good conductor.
Does the plastic become brittle on your...
So when we cool things, gang, they contract. Question?
In that plastic container?
Yeah.
Become brittle?
Yes.
It is very brittle. Very brittle. Yeah.
Don't
See the
drop.
frost on the outside? Yeah, if I drop that, it'll probably just crack a rooney. Hey, gang, I want to leave you with a question. When we cool things, they contract. When we heat things, they expand. If I heat this ring, get it really, really hot, and I'm going to do that next time. Next time I'm going to put it under the blowtorch, and I'm going to get it really, really hot. Will it become larger, smaller, or stay the same? Let's suppose we did this as a test. I took the ring, and let's suppose the ring right now will pass through the, let's suppose the ball will pass through the ring. If I heat the ball up, will it still pass through the ring? That's elementary. I would insult you if I told you to think about that for a long time, right? We know the ball's going to get bigger. And if the ball gets bigger, it'll never get through the hole if it just barely makes it now. Isn't that true? Here's the question I got for you. Next time we come in, I'm not going to heat up the ball. I'm going to heat up the ring. And when I heat up the ring, will the ball be able to get through if it just gets through now? Will the hole become larger, smaller, or stay the same size when I heat the ring? Think about that, because we got that for homework. Hey, you know what? You can do this as a test, experiment. Take a ring off your finger. Put it on the stove. Get it hot. Does the hole get bigger, smaller, or stay the same? And then jam it back on your finger and see. No, not your finger, your kid sister's finger, all right? Okay? And see if the hole gets larger, smaller, or stays the same. And see if you can say HC. For next time, gang. Okay? That's a homework. Catch you later. Physics.